Hello everyone, this is a video for your first quiz's question 3, right? This question is pretty much a Math 2901 question, right? But we're going through it because it might pop up in your final exam. You might need to revise some kind of techniques in this. And it's basically you have two independent variables that follow both chi-squared distributions, something you see along this course. And it turns out if you find this ratio that it's FMN. Right, so the standard technique for this time equation is that since this transform involves two random variables, so x and y, you're going to have to use a distribution that has two random variables, right? Because you can't use a single variable transformation. So what you're going to do is you're going to define two random variables, u and v, as a function of x and y, right? Some function. And you're going to make one of them the thing you want. So you're going to make, in this case, I'm going to make x on m over y on n, and v just a dummy variable. In this case, I'll make it y. Right, so that's your ultimate goal, right? You have the joint distribution that you're going to transform to, and then you just need to isolate the u afterwards, right? So the transform formula, if you guys don't remember, is this. So your target distribution is a function of your original distribution multiplied by the derivative of the original variables with respect to the new variables. Right, and the easy way to remember is just match the variables on each side with the numerator. Right, because you can kind of think of it naively if you were to integrate both sides, right, and bring this thing over, they both should integrate to 1. So that's kind of how I remember it. Because if it was like dxy here, instead, this thing wouldn't necessarily integrate to 1, right? And since they're PDFs, they should integrate to 1, right? So that's kind of just how I remember it, to this shenanigans over here. So obviously we need to find what this blue part is. So, but before we do that, I'll just kind of simplify this fxy shenanigans over here. So we know that x and y follow this particular distribution and they're independent, so it's pretty easy to find the joint distribution. Just multiply the two individuals. So I'll just do that. So x follows gamma, chi-squared m, and that's the same as gamma m on 2. So I'll just kind of write out the coefficients are and stuff like that. 2m on 2. m on 2, x, m on 2 minus 1, exponential negative x on 2, times by 1 on gamma n on 2, times 1 on 2 n on 2, x on y, because it's the y distribution now, y n on 2 minus 1, exponential negative y on 2. Right, and you have this blue blob over here that I haven't figured out yet. Right, now the reason why I kind of wrote this out for now is to show you that if you actually look at the terms in the function, the most important terms are the ones that involve x and y, or essentially your random variables, because everything else, so actually it's a different color, these purple parts, they're just flavor flavor values that makes it integrate to 1. Right, so ultimately they're not really that important in the form of the distribution. So knowing this, you just focus on the parts that contain x and y. Right, x and y. So you just do x m on 2 minus 1, x negative x on 2, y n on 2 minus 1, x negative y on 2, and then you just times by this circle thing that we haven't found yet. Right, so we need to find what this circle thing is. So this circle thing, we know the relationship between u and v up here. We define it as such. So all you need to do is find the Jacobian with respect to u and v, right, of x and y. But in this case, we have u and v as functions of x and y. right? So it's easier to do the reciprocal of this function, right? So it's easier to find, in fact, is equal to u and v x on y reciprocal, right? It's easy to do that because you already have the u and v in terms of x and y already, right? And if you kind of just do the Jacobian shenanigans, so I'll do it like right over here real quick, just differentiate it, you'll get n on my, right? Because I differentiate u respect to x, u respect to x. Next, I'll differentiate v respect to x, but since v is just y, so that's just 0. Do the same thing over here. Now you differentiate respect to y on this column, the second column. You get negative x y squared, and this is 1 because v is just y. You have to invert this, and you can see that this is just diagonal, and you can see you have to invert, so it's just my on n. Right, so my circle thing is actually my on n. And you can see by a similar argument, this m on n thing doesn't really contribute, isn't really significant to the function, right? So I just make it y, because all it does is makes the integrate to 1, right? And if you're trying to recognize the distribution, you really just need to recognize the parts that are like in terms of x and y. Right, so we have broken down the values, as you can see here. Now, since our left-hand side is actually a distribution in terms of u and v, you actually want to represent your right-hand side in terms of u and v as well, right? So, looking at this above transformation, you can see that since u equals to x nx over my and v equals to y, right? You can replace y pretty easily, just make it v. X, you need to kind of work a little bit, just do some rearranging. So x here equals to muv, because y and v are the same, over n, right? And so where we see x, you just replace it with this thing. Where we see y, you just replace it with this thing. Whoops, wrong way around. I should probably write it that way. Y equals to x, v. Replace it with this thing. Right, so I'll do that. This equals to muv over n to the power of m on 2 minus 1. Right, so as you can see, I replaced the x respect with this, okay, that's what's happening over here. X with this thing over here, right, just square thing. And I do the same thing with this exponential part as well, because it's also in terms of x, muv over 2n. Y is just v, so it's pretty straightforward. There's a y over here, so the power just adds up. And it's just exponential negative v on 2. Alright, now if you observe this again, you try to remove any unnecessary coefficients, because it makes your calculations easier. You notice that this m and n thing, you can just remove it, because it's just a constant, right? It's like a 2 essentially, right? So you can kind of just get rid of it. So you just uv. Because this power thing doesn't depend on u or v. So it's fine. Everything else you can't really break down any further. Right? Now, we have to remember our original purpose of doing all this in the first place. We want to find a distribution of u. Right? So you want to isolate u, essentially. So you want to integrate out v. So we're going to we're going to group up the u's and v's, right? So the u's in this case is just u to the power of m on 2 minus 1 from this. You can see that since this thing involves u and v, you can't separate it. And since you want to integrate out v, you kind of have to group it with the v's. Right, so this v thing over here, you can see this powers up with this. So m plus n on 2 minus 1. And you can see over here, these exponentials group up as well. 1 on 2n, mu plus m v, right? Just common denominator with the n. Right. Now, so you have this part over here. Since you want to find the distribution in terms of u only, you need to integrate out the v, so you need to integrate out the range of all possible values of v, so we need to know what v is. In this case, v is just the y random variable, and y is just chi-squared n, as you can see up here. So it's just 0 to infinity. So if you do this, so u to the power of m on 2 minus 1, integrate 0 to infinity. That's not an infinity, that looks, I know what that is. Okay, I don't know what that is either. I don't know what that is. Alright, what's happening? Alright, I'll take it. Anyway, you just write out all the terms, right? Just write it out. So NV dV. Right? This thing, oh wait, I should write proportional here, because technically it was always proportional. Everything I did earlier. Now, the thing is, if you actually look carefully at this thing looks hard to integrate, but you can see that V and V are here. And if you focus on the power terms, this thing and this thing over here is just your alpha. And this thing is your 1 on beta, right? And it looks like a gamma distribution, right? And these are your parameters. I said that in the wrong way around. But anyway, so this looks like a gamma distribution, and you can recognize the parameters, and you can see they're clearly positive, so it applies. So since you know this is a gamma distribution, right, or in the form of the gamma, all you need to do is find the coefficient such that it integrates to 1, right? And the reason why you have to do that in particular here, right, since the coefficient actually matters here, is because if you look at the beta term, this beta term depends on u, right? This beta has a u in it. So you kind of have to be careful here. So you need to introduce the coefficients here, unlike everywhere else I did up here, right? So if you recall the formula, I think it was, for you guys, it's, yeah. So it's gamma alpha with a beta alpha, right? This is the term that makes it integrate to 1, and obviously you need to balance it. So you just multiply by the other version, this thing. Right, and so this whole thing over here equals to 1. So this is equals to u to the power of m on 2 minus 1 beta. Beta here in this case is that. So you have times 2n over mu plus n to the power of alpha, so m plus n over 2. And this is gamma times gamma m plus n over 2. Right, so now you just want to focus on the parts that depend on u, because those are the most important parts in the PDF, right? You can see that this thing doesn't, so you can kind of just remove them. So you get u power of m on 2 minus 1 over, or times, 1 over mu plus n, because this 2n doesn't depend on u, and plus n over 2. Right. And if you were to actually kind of group things up a little bit more, 1 on u times by m over mu plus n to the power of m plus n, square roots. Right, if you look at this thing, right, so this is kind of your functional form, so the parts without the constant term that makes the integrate to 1. And if you were to go back to this thing, I'll bring it down all the way, if it would go down. Okay, bring it down, bring it down. If you look at this, right, if you just focus on the parts that are x, essentially, so this thing over here, with the square root, right, and x out here, you can see it's the same form, right? So your D1 here, D1, oh, I should use a different color. Okay, use purple. Your D1 is equal to m. As you can see, it corresponds at every point. D1, m, m. And your D2 is equal to n, because you can kind of see very clearly as well. D2, n, D2, n. Right? And since this thing must integrate to 1, the PDF must be this. And hence, you can see that. Hence, we have u equals to, I think it was nx over my, follows capital F, M, N, this particular distribution. Right, so that's how you would do it, right? It's mostly standard 2901 techniques, except it's multivariable, and you can kind of cut out the unnecessary fat, so like removing the coefficients because they're not really that important in the grand scheme of things, right? But you need to be careful when you reach the integrating step, in particular, because the coefficients you bring it back into the fray. Okay, the coefficients you bring in may contain the variable you're interested in. So as you can see here, this contains u, so you still include it. Whereas this gamma shenanigans over here doesn't depend on u, so you can just remove it again as well. Alright, and over here at the end, it's just kind of looking at it and go like, oh yeah, this looks like something else. Right, and you're good to go. So that's how you do this question basically. Alright, you just recognize that form.